Hello again, students. So, during the course of this lecture, I'm going to prove some results about the continuity of power series. So let's go ahead and get started. I'm going to prove this theorem. Theorem 4.5.4. Let ak be a sequence of real numbers. Let f of x be the series of ak's times x to the k's. Let r be the radius of convergence of f as defined above. If r is equal to infinity, then f is continuous on r. If 0 is less than r is less than infinity, then f is continuous on the open interval from negative r to r. Notice that since the domain is maybe not equal to this, the domain is maybe a little bit bigger, might be something like that, this doesn't tell us if it's continuous at the endpoints of the domain, if the domain even contains its endpoints. It turns out then the f will be continuous at the endpoints if it's defined at the endpoints, but we will not hit that in this lecture, in this class at all, because this is going to be the last of the lectures. So let's prove that. Let's let ak be a sequence of functions. F of x be the power series, the sum from k equals 0 to infinity of akx to the k. Let r be the radius of convergence of f. And here is what I will remind you of from proposition 4.5.2, which you should remember because you should have watched this just seconds ago. Proposition 4.5.2 says that if absolute value of p is less than that radius of convergence, then the series of ak p to the k, so if you like f of p, converges absolutely. It's not how you spell absolutely. That's okay. And it says that if the absolute value of p is bigger than r, then the series ak p to the k diverges. So, remembering that, there are going to be three claims. One claim when r is equal to 0, one claim when r is infinity, and one claim when r is neither 0 nor infinity. So the claim when r is 0 is trivial. When r happens to be 0, the function f is only defined at 0. And in fact, if you take a look at this, if you try to plug in x equals 0, what will you get? You'll get a0 times x to the 0, which is 1, plus 0 plus 0 plus 0 plus 0, and so on. Yeah, that converges. It converges to a0. So 0 is in the domain. Nothing else is. Because anything else would have absolute value of p bigger than 0. So the series would diverge at p. So the domain only contains singleton 0. But notice, singleton 0 is in singleton 0 and is an isolated point of singleton 0. Any function is always continuous at an isolated point of the domain. So f is continuous at 0. That's done when... So the statement here, and f is continuous at 0, is basically contentless. Any function that's defined only at 0 will automatically be continuous at 0 because 0 will be an isolated point. The other two will have very similar proofs to each other, not to what we just did. There's actual content. I'll give the proof in the case that 0 is less than r is less than infinity, and then I'll just say some words about how to modify it when r is equal to infinity. So let's assume that 0 is less than r is less than infinity, and consider any x in the open interval from negative r to positive r. I need to show that f is continuous at x. Well, let's come up with a choice of p that is somewhere between the absolute value of x and r. Well, you know a way of coming up with such a number. How about the number that's halfway between absolute value of x and r? Let's let p be the midpoint. Absolute value of x plus r over 2. Then I'll know that the absolute value of x is less than p. Since p is less than r, I can appeal to proposition 4.5.2 to conclude that the sum of a bunch of things that look like ak times p to the k equals 0 to infinity, converges absolutely. By expanding the definition of absolute convergence, I see what that means. That means that the sum from k equals 0 to infinity of absolute value of ak p to the k converges. Now, here's the way I'm going to proceed. I'm not going to try to come up with like a direct epsilon and epsilon delta proof for continuity. That would be too hard. Instead, I'm going to try to do this. I'm going to try to use the M series test to get the series of ak x to the k, y to the k. Right, the x kind of has a job already. To be to converge uniformly on negative p to p. If I can do that, then the series itself will be defined and will be the uniform limit of a sequence of continuous functions. Why continuous? Well, if I stop at n, then this is a degree n polynomial, which is continuous. So this thing will be a uniform limit of a sequence of continuous functions. Such things are continuous. That'll give continuity from negative p to positive p. But because of our choice of p, because of this, I'll know that x is interior to that interval. So I'll know that the function is continuous on this bigger set, which contains x in its interior. And that will give me that the function is continuous at x. Since x was chosen arbitrarily, I'll know that the sucker is continuous everywhere. So let's go ahead and make that happen. So let's consider any y in the interval from negative p to positive p, so the absolute value of y is less than or equal to p. But that means that the absolute value of ak times y to the k is less than or equal to the absolute value of ak times p to the k. If you want to go off to the side and check that, go for it. By the Weierstrass M-series test, I can now conclude, well, let's actually say why we get all of the hypotheses of the Weierstrass M-series test. So to appeal to the Weierstrass M-series test, I need to know that for every choice of y, I have an inequality like this, and that the series when I add up these terms converges. Well, I have that. I have this inequality. So, by the Weierstrass M-series test, I conclude that this series is uniformly convergent, at least on negative p to positive p, the closed interval from negative p to positive p. Thus, on the interval from negative p to positive p, the function f, which remember is the power series, is the limit of a uniformly convergent sequence of continuous functions. But that means it's the uniform limit of a sequence of continuous functions. We can therefore conclude that f is continuous on the interval from negative p to positive p, but x is interior to the interval from negative p to positive p, so that means that f is continuous at x. So let's just summarize. We have now proven that for every x in the open interval from negative r to positive r, f is continuous at x. I can conclude that f is continuous on negative r to r. So let's see what you would need to do if you wanted to make this proof work when r was infinite. So we certainly couldn't do this. Absolute value of x plus r over 2 would then be infinity, which isn't a number. So I can't ask about convergence there. But, well, let's just look at this. This color. So to make this proof work, I just needed a choice of p that was bigger than the absolute value of x. I need a choice of p such that absolute value of x is less than p, is less than infinity, but that's something you don't even need to write down. Any number will be less than infinity. So I just need something that's bigger than the absolute value of x. Pick your favorite way of taking a positive number and making it positive. Multiply it by 2 if you want. Add 1 to it if you want. I'll take p to be the absolute value of x plus 1. And then let's see if everything works out. P is less than infinity, so by proposition 4.5.2, you get this absolute convergence. So, because the series converges absolutely, I get this result. For any y between negative p and p, which x is, I get this inequality. So I can appeal to the Weierstrass M-series test. The rest of the proof is going to go through exactly the same. Cool. So that completes the proof of theorem 4.5.4, saying that power series are continuous. This is the final lecture that we'll give. There will be a few days more of class in which I'll expect you guys to put finishing touches on your benchmarks if you haven't finished them already, and get finished your final projects for real analysis. Wonderful then. I'll talk to you real soon. You have a good day.